because I'm not sure I'm ready for Fry to go on to next to greater things. I remember Fry from before they even started at Lawrence. They came to Lawrence as part of the Summer Institute and spent a day visiting labs, and they came back to Lawrence as my advisee, and I was like, I know you. Where do I know you from? And since that time, I just feel so privileged to have had Fry in my lab, as an advisee, as a student, and as what I would say a friend. They have helped me grow as a person, and I hope that I have helped them as well. So, yeah, they have done some wonderful work for me in my lab, and they're going to show you just a small part of what we have worked on together in Pennsylvania over the summer. But yeah, they have grown so much, and I am so proud of them, and I am privileged to be able to have been part of their journey here at Lawrence. Take it away, Fred.
Don't mind me if I choke up, but hi, I'm Brian. Show my pronouns are they, them, theirs, and I'm going to talk to you about my last summer's research with mapping ozone and methane in western Pennsylvania around natural gas wells. Now let's think about why this all even matters. Well, for one, we have to think about what methane does in our air. First, it contributes to global warming, and it also affects our health, which I'll get into later. But let's think about what methane is. By itself, it's one carbon with 4 hydrogens on it. It is a greenhouse gas, so a gas that traps some heat in our atmosphere, and has a 25-to-1 global warming potential factor compared to CO2s. So this means that 1 ton of methane compared to 1 ton of carbon dioxide has a 25 times higher potency at contributing to climate change. And according to the International Panel on Climate Change, back in 2018, so just last year, this report names methane as an important gas species. And natural gas is mostly methane. So what I mean by this is that 70% to 100% of natural gas is methane. So throughout this talk, I'll be switching between terms, and they can be used interchangeably between natural gas and methane. So when I was talking about health effects, it has to do with this equation. And I'm going to spare you all slides upon slides and arrows and a lot from the mechanism that methane takes part in for ozone. So every part of this equation is necessary. It starts off with sunlight, so we need to have time of day where there's sun. And then this NO2 species, where I'll call it NOx, because this gives us both NO2 and NO, since NO can be rapidly and readily converted back into NO2. And this comes from vehicle emissions. So in areas where there's a huge density of people using vehicles, we can have an environment conducive for this equation. And then we have our methane component. We can recognize the 1 carbon with the 4 hydrogens on it. This is a volatile organic compound. Volatile meaning that it's easily found in gas state, and an organic compound meaning that it has at least 1 carbon in it. So this is one sort of VOC. And from this, we get those 3 oxygens on the right side, showing ozone. Now, I'll recognize that, as most may have learned, that ozone is good for us. Well, that comes with a huge asterisk, so a huge condition, that ozone is only good up high, out of our breathing range, where it can have a layer to protect us from the UV radiation from the sun. But down low, where we're breathing it, it is detrimental to our health and even damages plants. And, see in this picture, it is the main component of smog, which is bad for our breathing, and we really just don't want it near us. So we have to think about, how do we contribute to methane emissions to create this sort of environment for smog? Well, we can think about the human sources of methane out of the total US methane emissions. One of these human sources is enteric fermentation, which has 27% out of total US methane emissions. And I know this doesn't look like a human, but we contribute to their population because of our high demand for beef and cheese and other dairy products. So if we think to our last cheeseburger or our last milkshake, that gives us demand for needing more of them and contributing to methane emissions. Another source would be with landfills. At 16% of the total U.S. methane emissions, we have our waste that we directly put into these landfills and contribute to our emissions. And 26% would be a lot of other smaller components, so natural sources and smaller human sources of methane. But the main focus of this talk is around natural gas and petroleum systems, where we contribute 31% from this. And some of us may have heard, like on YouTube ads or in the news, that natural gas is the cleaner energy source, but this is only true if we keep the leaks that happen in these infrastructures down to 3.4%. So how much methane do we actually use since we draw our energy from there? Well, at 34% are in light blue. We have a lot of other sources, so smaller sources. And at 37%, we have petroleum in green. And in yellow, we have 29% for natural gas. So a majority of this pie is from these systems. A majority of this pie, meaning a majority of what we get our energy from, are from these systems. Now, according to the U.S. Energy Information Administration, or the EIA, this whole pie gives us 97.7 quadrillion British thermal units, or BTUs, where one BTU is equivalent to the energy of burning one match. And I can just put 97.7 quadrillion up on the screen, but it's very important to conceptualize the magnitude of what that means. So let's start with this analogy. If we imagine this tiny speck, even almost near the size of a needle prick on your finger, is 1 cubic millimeter. Now, if we multiply that by 1,000, we have a sizable cube that can fit in the palm of our hand. But now let's just jump to quadrillion. It may be a little hard to see in this picture, but near this needle and the sides of many of these tall buildings is our quadrillion cubic millimeters. So if we can imagine, or even attempt to imagine, 97.7 quadrillion matches burning off and giving us energy, that is how much we are consuming in the US. Now, when I'm talking about these systems, when I'm saying the natural gas system specifically, we can see we start at the gas field where we have this pipe, which is just a picture of an abandoned pipe, and this can look differently depending on how they want to extract natural gas. And then it goes to the processing stage where it refines the resources that we're going to use, and they transport it in the transmission stage on boats, cars, through pipes, right to our front door, where we're using it to charge our phones, feed our houses, etc. And at any point along this, there could be leaks happening. And this is not the shortest process, so it can span a huge distance. Now, what can these leaks look like within these systems? Well, they can look like a crack in this pipe, a break in the seal, even a hole in maybe these storage units. It can also look like the picture we saw earlier with the pipe. There could be an abandoned pipe that went to natural gas, and sometimes it can even be underground leaks, causing methane to rise to the surface. These leaks are costly since it's not going directly to our energy consumption. They happen a lot of the time, more often than is estimated at some points, and they contribute a great amount of methane emissions to drive factors to global warming and air quality if we can remember back to the smog. Now, how much methane is actually coming out from this process? Well, the total 2016 oil and gas methane emissions says that it's about 202 metric megatons of CO2. So let's also try to conceptualize this quantity. If you can see in this picture with a bunch of tiny smiling faces around this giant inflated 1 ton of carbon dioxide, we can try to imagine having multiplied this by 10 to the 6th, or to get to the megaton. I cannot even begin to try to fill this page to get there, but I hope you get the picture. So, what are the emissions? By each step, we can see this pie chart breaks up which parts the methane emissions would be coming out of. So the processing, transmission, distribution, and oil production. but at a whopping 53%, so a majority of this pie, and the majority of those giant balloons, we have gas fields. It's important to remember about these leaks that they are unintended and underestimated sources of methane emissions. So, where are we getting this natural gas since we depend so heavily on it? Well, we can get them from different sorts of wells. And according to the U.S. natural gas gross withdrawals by well type, we have the years from 2007 to 2013 on the x-axis, and natural gas withdrawal in terms of billion cubic feet per day. You can see that on the right, there are the types of gas wells, and the bottom three, they somewhat remain somewhat consistent, if not decreasing, in gas withdrawals, while shale gas wells in blue are on a rapid rise from 2007 to 2013. That's just within 6 years. So we should begin to wonder, where are we getting this shale? Well, what is shale? Shale starts a long time ago where organic matter such as dead plants or other organisms settle onto sediment, and over another long period of time, more sediment builds up on top of this, really putting in the organic material and the sediment. And even more time passes and more pressure is put on this layer, so we can get shale, which looks like this. And as you can see, shale can hold oil and natural gas, where the shale gas wells extract the resources from. So what are these wells? Well, I want to start by saying, working with Deanna for the past how many years? You get to know that she's really good at baking, so I hope we have a good sweet analogy to bite into here. So we have, on our left, conventional wells, where you can think of it as a sort of jelly donut sort of well, where you can drill straight down and into a pocket of natural gas and extract it. And on our right are the unconventional well types, where this is a sort of younger technology compared to the conventional well, where, using this analogy, you have different layers, such as different layers of the earth, and we can get to this sweet, soft, bready layer that can hold a lot of moisture. And this, in this picture, would resemble the shale layer, where the conventional well type drills straight down, and then once it reaches that shale layer, drills across horizontally in order to maximize the natural gas extraction. Well, now that we know some of the well types, where can we find them? We have to go to shale formations, and one point of interest would be the northeastern part of the United States, where in blue, we have the Utica Shale Formation. Light green around West Virginia, we have the Marcellus Shale Formation, and in dark green, we have the Utica underlying the Marcellus, so a point where the Marcellus is over the Utica Shale Formations, which makes it a prime spot to tap into for natural gas. And when you're trying to think of how many there are, we can see in red X's the conventional wells, or the jelly donut wells, which not only gather natural gas from shale, but other sorts of pockets. And in blue X's, we have unconventional wells, or tiramisu wells. And just looking at this figure, each X is so tiny, but there are huge blotches of blue and red all over the page, and even some blue underlying this red. And this goes to show us over 100,000 natural gas wells can be found in this part of the state. And it has a long history of drilling natural gas, coal, and oil. But in this figure, we're only focusing on the natural gas drilling. And this is just natural gas wells shown here. And just from the sheer plethora of natural gas wells there are, you can go in someone's backyard and just trip over a wellhead, or do what I did over the summer and on short car trips, try to look out the window and try to spot how many wellheads there are within your 15-minute drive. And even without my glasses, I could see a few of them, like maybe 6 on a 15-minute ride, and I could be a staggering distance away from them. And emissions can happen all around these sites because there's such a huge number of wells here. Emissions would be happening in different areas. So we want to focus on certain emitters, the super emitters. And to explain what a super emitter is, you can look at the number of sites on the x-axis and then the amount of methane emissions on the y. And if we look around this 40 percentile, this 40% contributes to almost 0% of the total methane emissions. While, as we follow along the x-axis and up to this dotted line, this last 5% of emitters, at that 95% to 100, so 5%, contributes to about 30% of methane emissions. So a few number of these emitters contribute to a large amount of the methane. So far, what do we know? Well, one, methane has 1 carbon, 4 hydrogens. It contributes to global warming and smog that affects our health. You can find a lot of natural gas wells in Pennsylvania, so it would be a very great spot to go to do our research. And we should be targeting and figuring out how to target super emitters. So how do you find and characterize these leaks? Well, one, you can locate them by methane detection. And this is mostly a method used by atmospheric chemists by going and using methane detection. We can also characterize with flow meters, which is predominantly used with geologists and the industry. So when we collaborated with the Indiana University of Pennsylvania, we were able to work with some geologists and able to combine our efforts to better characterize these leaks or emissions. And on the bottom right, this is one of our collaborators, Steve Hoven, pointing out the brown arrow-looking pipe out of the ground, and that would be one of the natural gas wells. So how are we specifically investigating leaks? What did our team do? Well, we used a backpack platform. And this backpack platform is super important because if we remember the sheer plethora of wells all over the state, they could be within wilderness areas where leaks can happen and people might not even notice. And it would be hard to drive a car maybe through a 2-foot wide clearing in the trees. So on-foot mobility would be important to investigate these leaks that may go unnoticed and could be super emitters. Now, what's in this backpack? Well, one, it was a lot of fun to put together, not gonna lie. I have not played with PVC pipes in a while, but it was important to use that for building up this platform. So with this backpack platform, it has a solar panel seen on the back here, where it prolongs battery life for longer field deployments, because nothing would hurt me more than going on a 3-mile trek maybe and using this platform, and when I'm getting to a cool source, it just dying on me, because that would suck. And since it's a backpack, we have that on-foot mobility in order to get to these less accessible sites. And on the bottom in the black suitcase-looking device, we have our natural gas monitor, which samples at 1 second, and it has a mid-IR spectroscopy in order to detect natural gas. And on the bottom right in blue, we have our ozone monitor that samples at 2 seconds and uses UV spectroscopy. And finally, a GPS device, where we can combine the data from the natural gas ozone and GPS device to see at the spot that we're at this specific time how much natural gas and ozone is in this area. But first, we want to know if this even worked. So we grabbed the backpack platform and headed out to a site called the Robert Shaw. And it's this central building where it was supposed to be a daycare. They had the building ready, they were about to send little kids in, but then when they tested the air, it had dangerous amounts of methane that children should not be around, and even to maybe explosive levels. So we want to see if we can spot the source of this leak, because we knew it was in this area, but they didn't tell us specifically where. So we hopped in Dan's car since it was easiest to go around this area. And we stuck the tube out the window, still in the backpack platform, and gathered data on methane. So in blue, in cooler colors, we have background amounts of methane, so just baseline amounts. And in warmer colors, like in going up to red, we have higher amounts of methane. And especially seen around this red star, we can see peaks of methane. So we're getting close to the source, and the source would be right around here, where we saw a lot of methane just at that one point. So since we found out it worked, we want to set a standard method for sampling. So I put on the backpack and walked around the IUP green, and it would just be standardizing how long my strides were per distance, And since I'm lacking a little bit of depth perception, it was a little hard to try to get the sampling a certain amount of inches above the ground, but luckily I finally got to a point where I can remember what it feels like to hold it above that distance and see it. So we want to take it and go to a site where we can maybe find a suspected. Thanks to a collaborator at the beginning of the summer, told us about this one spot on a hiking trail that I won't reveal where, since for legal reasons. And this is what he saw. If you can see the bubbling happening around that part of the puddle, he thought he smelled natural gas in the site. So we wanted to see what we were dealing with and if there's natural gas. But this was before we had our methane monitor, and sadly not the backpack platform even. So we went there and just to check it out with other collaborators. And we found that maybe there was some natural gas, but nothing that we can actually use for data. But thankfully, in the last part of the summer, in the last 2 weeks, we got our methane monitor, and thus the backpack platform. And it took a little bit just for manufacturing issues, but thanks to Deanna's determination, we were able to get a loaner instruments that we saw earlier. So, thanks to this site, I got to practice a almost 3-mile graduation walk through this trail, where I took careful timed steps and kept the sampling rod a certain distance above the ground. And what did we find? Well, in red, we can see background levels of methane, and in blue, these are basically markers for showing us where natural gas can be detected. And if we zoom in along this trail, we have this bundle where you can see a lot more of these blue dots, telling us that there's sources of methane here. So if we look at the data we got with this, our methane map, where blue in this case is the lower background levels, and in warmer colors, we have higher amounts of methane. Cool. We were able to see more methane sources around this area, and in cooler colors, more background levels of methane. But when we compare it to our ozone map, we saw that around the same area that they were source methane, there were less concentrations of ozone. And at the beginning, where there would be less methane detected, there would be some more ozone. Now, how does this fit with the mechanism that we saw earlier? Well, maybe there wasn't enough NOx in this environment, and you have to take into account mixing. Mixing is when there's no chemical processes, and the air is just diffusing around and just physically moving throughout the area. So we want to take this into account, and try to account for this by using the ratio of change in ozone over change in methane. And when we put it here, the one ratio, which was our mixing, is in this pale yellowish, almost white color. And in a darker color, so in your blue, we had a decreased amount of ozone or an increase of methane in this area, especially around the source. And in the top part of this figure, we have warmer colors where there could be higher amounts of ozone or lower amounts of methane. And we want to test and see this platform used at a different site. Well, here was our source. And this is where we saw mixings with that one ratio. And here we need to look at and understand a little bit more, since there was a lot of different mechanisms and concentration changes in this area. So when we looked at another site with one known methane source, that is the well pipe, and if we remember earlier in the picture of Steve Hoven, I have blue airs coming out near this wellhead in order to show that methane is coming out through these pipes. And when Steve Hoven was trying to characterize this using flow meters, he plugged one end of this and read through the other, and he found that there's 3 to 17 liters per minute coming out of this wellhead, which is a lot. And this qualifies as a super. So when we expected to look at this, We have the distance from the wellhead in meters on our x-axis and the change of methane concentration from the background on our y. And if we have ideal conditions and mostly just mixing, we would expect to see a trend that follows this green line. But what we actually got was a little bit different. As we were at 0, we would have expected to see a lot more methane near the wellhead, but we saw a lot more methane at around 5 meters. So maybe the methane could have just diffused at that point and pocketed in that area. And it's important to note that the different colors on this figure show different sites. And you may not be able to see it because it's pretty small and near 0. All of these tiny boxes that tell us that this is an out of plume data or have a lower average of methane at those times. While the ones that we can see here, the bolder colors, are where there's in plume data, so when there's a higher concentration of methane. So when we looked at ozone, and we can see the in plume and out of plume boxes here, with the in plume being on the left of each pair, and out of plume data, which is on the right, so the lighter colors on each pair. We got this here. We expected to see what would follow along this solid blue line, where near the wellhead there would just be a lot more methane, and see maybe a sort of drop off for the concentration of ozone around this point. And what we actually got was following along this dotted line, where we can see around the same spots that we saw in the last figure at around 15 meters and 27 meters, there was still some methane. Well, we can see some ozone being decreasing here. So what trends are we looking for when we use the change in ozone over change in methane ratio? Well, we expect to see mixing. So the no chemical processing, where the ratio equals 1. And on top in light blue, we would expect to see the production of ozone, or destruction of methane. And if it's below this 1 ratio, we would have destruction of ozone, since we know the source of methane, and it wouldn't be produced as we're going farther away from it as well. So, what are we able to see? Well, these boxes are the out of plume data, and give us the 1 ratio just for mixing. Meanwhile, in our in plume data, we were able to see a different sort of story, where at this point we have destruction of ozone, and at this part there's production of ozone, so the slight decrease there. And moving forward, we want to see more about how this chemical mechanism works. So to conclude the research that we did this summer, we have a backpack platform that works at detecting some trace methane. This is a great first qualifier for this research. And it offers mapping opportunities that aid in what they need in Pennsylvania, since they have such a huge amount of natural gas infrastructure. And this is a platform that can compare in situ, so at that point, at that time, natural gas and ozone concentrations. And more research is necessary around inventorying natural gas leaks. So what are the next steps? The next step would be analyzing all the data collected from the campaign. Since we had such a rapid sampling time, we have a lot of data points to go through. And there could be a possible return to the area to collect more data in the winter, since seasonal changes could affect what we would be seeing. And we could work on observing more of the methane and ozone relationships in a given area. And I would like to thank Deanna Donahue, Elizabeth Bridgewater, Steve Hoban, Katie Farnsworth, Cindy Rogers, Katie Kitzinger, and Crane Korn, Daniel Martin, Lawrence University, and the NASA Wisconsin Space Grant Consortium. There are my references. And thank you for listening. Thanks for coming.
So in some of the last figures you talked about like plumes, and maybe you defined this and I missed it, but can you just elaborate on like what a plume is? That just like a source where you have like a lot of methane coming in?
A plume, if you can imagine, is just the methane So a large amount of methane, when we can catch it during those concentrations, maybe the wind would be a factor, and if we're able to be within that air that has a lot of methane at that point in time. So a higher average of methane.
Can you go to your first plot with the methane lens? Yeah, that one. So for this plot, you were just measuring like pure methane gas.
Yeah, pretty much.
Okay. I was just curious, and I don't really know much about like the cycle to make ozone, but I'm wondering if it's possible if like closer to that wellhead, that methane is like technically there just in a different molecule because of the reaction process. Do you have any thoughts about that?
Well, I'd have to do a little bit more research on that, but there would be a lot of complicated cycling, and if we can, I'm not sure if you remember the mechanism when we learned over
Right, is that decrease real?
this decrease?
Is that lower levels at the first sites, are they real? Or are they a sampling artifact?
These would be a sampling artifact. So it would have a bias in terms of the, not a bias, but a sort of thing that happens during sampling that would skew it. So that's why we used this plot, because it accounts for that.
That decrease is just because of mixing, how we're catching the mixing.
Any other questions?
What made you decide to have the sampling wand, that certain height above the ground?
Well, we decided that's it's a good distance. Can't remember if it's like 6 inches, 5 inches maybe, but it was high enough so that we're not sucking in a lot of the dirt just coming off the ground, but low enough in order to detect these possible leaks that could be bubbling up from underground emissions.
And then with the follow-up, when you were near known wells, were you sampling to, like, so the picture with the sort of arrow-looking wellhead, did you use that same sampling height when you were at wells like that, or did you do the sampling differently?
We did the sampling differently. So with the sampling rod, we had it still relatively higher than the backpack in order to be that certain distance away from the wellhead. Since we used another platform there too.
Let's thank our speaker again.